Welcome again to the Winchester weekend. In the Winchester weekend for the last few years, we've introduced the idea of a taste of a section. So we've had solar, lunar, all the sections, and one we've tried to put on in the last couple of years, but we failed because of problems, was our increased interest in exoplanets. And Roger Dimmick has been trying to promote in the association that the amateur can be involved in exoplanets for the last few years, and he's successfully launched and runs the subsection of the dealing with minor planets. So the rest of the Winchester weekend will, if you can see a theme, the main talks are all going to be on exoplanets. So let's start with Roger and your take over and introduce your speakers. Thank you very much.
Right, good afternoon one and all. Welcome to Dr. David Brown's Warm Up Act. And my thanks to Ann Davis for organising this day, and to David, who has kindly given this presentation the once over. So if there are any mistakes in it, they're all his fault. Not really. It would be nice if it actually moved on. Let me try again. Ah, that's better, right. The two screens, you've got to make sure you've got the cursor on the right screen. Research in exoplanets is moving from the age of discovery, transit photometry, upper left is one method of doing this, to characterization. Bottom left shows a graph of planetary mass against radius. The measurements of mass, radius, orbital inclination by transit and radial velocity methods can define density and possible planetary structure, for example, gaseous or rocky. Currently, such measurements are not precise enough to do this with a large amount of certainty. Future space and ground-based missions should enable a much greater accuracy to be obtained. The spectrum on top right is what we'll use to search for biomarkers in the atmospheres of exoplanets by spectroscopy, which might indicate the presence of life. The ultimate aim, of course, is to answer the question, is there life elsewhere? Whether the infamous Martian worm in the bottom right-hand corner is an example of that is still open to question. Right, who is watching? The various space missions and ground-based observers seeking to probe the makeup of exoplanets and their atmospheres are listed here. There are quite a number of other missions, both space and ground-based, observing exoplanets, both full and part-time. But I will briefly describe these. So just a commercial, if anyone's interested in this, I do have a longer presentation on the subject, which has been kindly vetted and much improved by Professor Don Polarco. Top left, you have an impression of a very large exoplanet, WASP-79b, which is 286 times as large as the Earth. Bottom right is a very small one, Kepler 37b, which is only 0.3 Earth radii. So you can see what a large range of sizes there are as far as exoplanets are concerned. And for the younger ones amongst you, that's comedians little and large in the middle. So the first one I'll talk about is Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Must have taken some time to dream up that name. It's a European Space Agency mission, and it will investigate the atmospheres of mainly hot, large exoplanets in order to understand how planetary systems form and evolve. And it's scheduled to launch in 2029. So some of you may still be around then. Ariel needs up-to-date ephemerides of exoplanet transits to ensure it's pointing at the right target at the right time and that transits are not missed. BAA members are participating in this project by imaging transits and posting results on the Exoclock website. Got two examples here. On the left is one taken by Steve Future and Portsmouth University students using the Hampshire Astronomical Group's 24-inch telescope. The one on the right is by myself, which uses a 6-inch robotic telescope out in Arizona. So you can see the range of telescopes you can use to observe these exoplanet transits. Another European mission is Plato, Planetary Transits and Oscillations of Stars. Its objectives are listed here in summary: to find and study extrasolar planetary systems with emphasis on the properties of terrestrial planets in the habitable zones around Sun-like stars. It's scheduled to launch in 2026. There will be a role for amateurs to play to confirm Plato's discoveries, and we should know much more about this later this year. So that's two projects, Ariel and Plato. We are involved or can be involved in. Plato I've mentioned on the previous slide. The Transiting Exoplanet Survey Satellite, or TESS, the goal of that is to detect small planets around bright host stars in the solar neighborhood, and so that detailed characterizations of the planets and their atmospheres can be performed by the James Webb Space Telescope, which we assume will get launched sometime, and the European Extremely Large Telescope. This is the James Webb Space Telescope, an image, artist's impression with its sun shield stowed for launch. We just hope it will open out properly when it actually gets to its Lagrange point. Observing the infrared, it's not dedicated to exoplanets, and the other objectives are shown on this slide. The European Extremely Large Telescope is not dedicated to exoplanet observation, and the other objectives are shown here. So it'll be 2 or 3 years away before we actually get first light. I'm not sure whether this is the one that was the overwhelmingly large telescope, or that is yet to come. A Twinkle is a different kettle of fish. It will primarily be funded by the sale of telescope time, complemented by public grants, ESA and UK government money, and private investment. Again, it will use spectroscopy to reveal the chemical composition, weather, and history of exoplanets. It will be built in the UK and launched into a low Earth orbit early next year. And now a commercial for a possible future project for us. Gaia was launched in 2013, and its objectives include measuring the positions and brightness of about a billion stars, I should say, in our galaxy and other members of the local group. Top left, if a star passes between the Earth and a distant object, it will appear to brighten as shown in the center diagram. An associated exoplanet will cause a smaller magnitude increase as shown by the secondary peak. We hoped to launch a project soon to get involved with this work. And the imaging should be within the capabilities of a reasonably competent observer. We're working with a group in the University of Warsaw who's developed this Black Hole Tom website. It's nothing to do with black holes particularly. It was just a catchy name, they said, to get people's attention. But by using their target list and filtering it out, we may be able to, who knows, observe an exoplanet. As I mentioned earlier, there are many, many eyes on the exoplanet heavens. Looking at the top and middle rows, we have Ariel, Cheops, Plato, James Webb, Twinkle, and TESS. And at the bottom row, we've got ALMA, BLT, EELT, amateur astronomers, robotic telescopes, and even online surveys you can take part in. Not all of these, as I said, are dedicated to exoplanets all of the time, but amongst them we should know a great deal more about exoplanets than we do now over the next 10 years. But will any of them detect signs of life? And if they do, what will it look like? Right, that was a brief summary of where exoplanet research is going in the future. I didn't mention anything about Cheops. I think that's the way to pronounce it, not Cheops, Cheops, I believe. And I'll leave it up to our next speaker, Dr. David Brown, to tell you all about it. Just a brief intro. David studied physics at the University of Warwick and went on to study for a PhD at the University of St Andrews. After a short stint as a postdoctoral researcher at Queen's University, Belfast, he returned to the University of Warwick, first as a postdoc and more recently as a member of the astronomy staff. His primary research interest is the discovery and bulk characterization of exoplanetary systems. He was a member of the WASP project for nearly 10 years. These days, he primarily works on the development of ESA's Plato mission, but now he's going to tell us all about Cheops.
Thank you very much, Roger. Yes, there is one question in the Q&A, but I see Andrew is typing an answer.
Yes, I was just going to type it on, which was, I may as well say, yeah, I was just going to say, yeah, the owl was going to be a 100-meter telescope, yes, which then got shoved. That really would have been very impressive.
Yes, I think the engineering challenges involved in building the ELT are substantial enough at the moment without trying for a 100-meter telescope.
Maybe a couple of years' time.
Yeah, possibly.
Thanks.
Yes. Okay, let me close that down and share that. And then okay, hopefully you are seeing my slides. So yes, please do let me know, Roger or Andrew, if they're not working.
All looking good.
Thank you very much. Yes, thank you very much for the introduction, Roger. It's a real pleasure to be here speaking to you this afternoon, and it really is a shame that it can't be in person, as we all know. So as Roger said, I'm going to talk to you about Cheops or Cheops. I've heard both pronunciations from different members of the consortium, and it really is quite exciting to be talking to you about this mission. Of course, it is a European-wide mission. There are more than 100 scientists from 11 European countries that contribute to this mission. So it's a real team effort. And Roger's given quite a good introduction there to the various observatories and satellites that are involved in this field. I wanted to start, before I get on to talking about Cheops itself, to talk a little bit about the state of exoplanet research as a field. So this morning I went to the NASA Exoplanet Archive, which is a fantastic website. If you're not familiar with it, it gives you lists of all of the confirmed planets, and you can dig around in the data to look at their masses and their radii and various properties. And as of this morning, we are at 4,375 confirmed planets. Now, I could get into a long discussion about what a confirmed planet is versus a candidate versus a validated planet, but that would take a while, and I don't really have time to go into that. But we have this many planets confirmed. And this graph is a histogram, a cumulative histogram of the number of detections over time. So you can see it's a relatively young field as far as astronomical research goes. But you can see how it's grown over the years. It's been steadily steadily for the most part, ramping up over time. The different colors here represent different methods of detection. So the pink is radial velocities, and the green is transits. And so you can see how initially the field was dominated by radial velocity surveys, and then as ground-based telescopes and observatories started to come online, do their wide field surveys, transits really start to take over. And then you have the Kepler mission, which was responsible for the two big spikes here and here, which are, or were rather, large statistically confirmed and validated numbers of planet detections. And of course, now we're into the era of TESS and chaos, as Roger mentioned. One of the things we've really learned from these 4,375 systems is that variety is the spice of life here. So this slightly out of date video is of a large number of planetary systems discovered by Kepler. The orbits are to scale, so you have the solar system in the dashed lines and all of the exoplanet systems in the solid lines. The colors represent different surface temperatures, and the sizes of the circles indicate the relative radii of the planets. And what this shows is that we have a huge variety in the type of systems we see. You have compact systems of multiple planets like this one here. You've got a small number of planets close in and then something on a long, wide orbit accompanying it. You've got giant planets really close in, and apparently, as far as we know at the moment, nothing else. But there's nothing that's truly like the solar system. And that's a point I'll come back to towards the end of my presentation. If you have a look at planet radius against mass, this is a zoomed out version of the graph that Roger showed. He had some of the most well characterized systems. Here I've put everything that has both a radius and a true mass on it, with some of the solar system planets, so you can see where they are for comparison. And again, you can see that we've found quite a range of systems. We've got large gas planets up here, and we've got smaller, more terrestrial things, sort of ice giants as well. The Earth occupies this sort of slightly lonely or lonelier position. Mars down here, very lonely indeed. But we also have this set of planets over here, which are like nothing really in the solar system. Similarly, these giant planets up here as well, not really, they're heavier than Jupiter, they're more massive than Jupiter, but they are around the same kind of size. And we're seeing this variety, and what it's taught us really is that the solar system isn't the general rule, as implied by the video, the Kepler orrery that I showed. Small planets are not necessarily rocky. Large planets are not necessarily gaseous. We have lots of different classes of planets. We have things called mini Neptunes, super Earths. We have the hot Jupiters that were some of the first planets discovered around solar-like stars. We even have things that have been called super puff planets, where the planet is substantially larger than its mass might imply. And the reasons behind that are debated and not entirely clear, and probably vary from system to system as well. All of this basically means that if we really want to understand some of these systems, what we need is precise, accurate measurements of both their masses and their radii, if we want to know what these planets are really, really like. That's not an easy thing to do. You get the masses from one type of observation, you get those from radial velocities. You get the radii generally from transits. So you need to combine multiple types of observation here. But trying to get these precise measurements is really where CHAOPS comes in. So CHAOPS is the first small mission that the European Space Agency have put together. S here doesn't necessarily mean small. It is a relatively small budget. It's still a space mission, so it's expensive. But more sort of a better way to think about it is a shorter scale mission. So it's a slightly more accelerated development, slightly more accelerated timeline, and yes, that slightly smaller budget. CHAOPS is not only the first S-class mission, it's also the first space mission that's dedicated to studying known exoplanets. We've had Corot and Kepler and TESS, as seen on the top row of this timeline, but they were all really detection missions. Yes, Kepler and TESS particularly have observed known systems and have tried to learn about them in more detail, but that's mostly been as tests and as calibration for their processing, for their observations and their capabilities. Their primary function was new discoveries. CHAOPS can't do that, and I'll get to why in a minute. CHAOPS is a transit mission, so it's observing known exoplanets and looking for transits of those planets around their host stars. And it does so using a single telescope. So more along the lines of the Kepler model, the single telescope, than the 4-telescope TESS design. Here you can see the telescope to scale with the leader of the project of the CHAOPS consortium, Willy Benz. I won't label which one's which. And here's a slightly different view of the telescope. So it's a 30-centimeter mirror. So this is not a big telescope. If you compare it to Kepler, Kepler was a 95-centimeter mirror. So this is about 1/3 of the size. It has a 19 by 19 arc-minute field of view. So it's not a huge patch of sky compared to some exoplanet surveys. Again, that feeds into this or relates to this point that it is observing known systems rather than trying to discover new ones. It is, although it's smaller than Kepler, it is bigger than TESS. TESS's mirrors are 10.5 centimeters. And a lot of the successful ground-based observatories used 20-centimeter telescopes. So this is slightly bigger than those, but still a relatively small instrument. So CHAOPS uses this 30-centimeter telescope to observe transits with ultra-high precision. And it's measuring the size of planets whose mass is known. And the primary reason for this, as I've mentioned, is to try and investigate what planets are made of. If you can get a precise radius for that known mass, then you can start to get the bulk density of the objects. There's a whole zoo of possible types of planets between the sort of Earth and Neptune mass range. So I mentioned super Earths and mini Neptunes, they fit quite nicely into here. Gas dwarfs, ocean planets, and things like that. You also have this, this subclass between the ice giants and the gas giants, where you possibly have giant planets with massive cores. But really the focus of CHAOPS is more on that, this first gap here, where we don't have many any planets like this in the solar system. And as I said, by getting these radius measurements, we get the bulk density. Now, this doesn't inherently give us the ability to distinguish between these 4 different types of planets. We can't dig into the unique internal structures that these 4 types have. But what the bulk density represents is a key ingredient in our models that help us to then distinguish between these types of planets. So it's a necessary step, and it's an important step on the route to investigating internal structure. It can give you a rough idea as well. And as I said, to do this, we are trying to get as high precision observations as we can. That really is the key goal of CHAOSS, is that ultra high precision. So when CHAOSS was initially proposed in sort of 2012, 2013, this was its sort of key science goal, try and get precise densities for super Earths and mini Neptunes. The secondary goal was to try and find good targets for atmospheric characterization. So sort of feeding into the point Roger made about trying to investigate what is in the atmospheres of these planets to look potentially at habitability. And the initial strategy was half finding transits of planets that had been detected by radial velocity surveys. So planets who had not been observed to transit yet, but which might transit. From the radial velocity survey, you can model the orbit and then estimate when the transit should occur, and then try and observe that with CHAOSS. And then the other half of the time was to try and improve radius measurements of known transiting systems. So take things seen with ground-based surveys like WASP, HatNet, KELT, or NGTS, and try and improve the radius measurements. Now, these 2 goals imply that CHAOSS is a follow-up mission. So as I said earlier, it's not a detection mission, it's a characterization mission. So rather than looking at a large patch of the sky like Kepler or TESS, it points at a single target at a time, more like a traditional observatory. By its very nature, that overall strategy means that CHAOSS has to be quite flexible. It has to be able to adapt its observing strategy on the fly according to the science priorities of whatever targets it wishes to observe. That flexibility proved quite important because after CHAOSS was selected to be developed and pushed forward into an actual mission, the landscape of the exoplanet field changed quite considerably. So Spitzer was extended, the infrared observatory. After its coolant had been used, it was extended into the so-called warm Spitzer mission, where it continued observing for several years as it gradually warmed up. Kepler was repurposed into the K2 mission, where they stabilized it using the sun to achieve a bit of extra longevity. We've had Gaia launch, which is an absolutely fantastic mission for all kinds of astronomy. TESS has been selected and launched since CHAOSS was selected. And then we've had Plato and Ariel come along as well. So the whole landscape of the field has changed quite considerably in those intervening 8-9 years. And so what was initially planned as the science strategy for CHAOSS, this 50% of the time to find transits and 50% of the time to observe known transits, was rethought. And rather than this 50-50 split, the science team came up with a slightly broader strategy, where about half of the time is still spent on those two goals, but the other half of the time is spent on a range of other things that are enabled by the Cheops instrument. So there is a little bit of time in there for searching for new planets. That's not necessarily planets around stars that are not known to host planets. This is new planets in known systems. So a third planet where 2 are known, or a 4th planet where 3 are known, etc. Some time for observing exoplanet atmospheres and trying to see what you can do to detect various gases in the atmospheres of planets. A little bit of time for very small, subtle characteristics of planetary systems, things like moons or exoplanetary rings. These are very difficult to detect, and they rely on very subtle elements of a transit light curve, but they are theoretically possible to see. And then about a quarter of the time for other science. So there's a lot of things you can do when you have really good, precise photometry. You can investigate variability in some detail. You can try and improve your knowledge of exoplanet orbits, which lets you look at things like transit timing variations or orbits decaying as a planet spirals inwards towards its host. There's a lot of things you can do with that photometry once you have it. So a quarter of the time has now gone to that. Once we've agreed on this more broader program, the tricky thing is to work out how to schedule it. Because this is a satellite mission, you have to program in the observations, and you have to work out how to allocate the time fairly amongst the different science goals. So you're constrained by the timeshare that's allocated to each goal. You're restricted by the time that a particular program needs to perform its observations. You're restricted by the fact that transits, by their nature, are time sensitive. You have to observe a transit when it happens. You can't just go and look to see one whenever you like. But you're also constrained by the fact that Cheops is in low Earth orbit. So a bit like Hubble, the Hubble Space Telescope, Cheops has to deal with the Earth sometimes being in the way of what you want to see. And that places its own constraints on covering a particular transit event. So to try and deal with all of these different constraints, Cheops uses an automated planning software, which is built on some quite clever genetic algorithms to optimize everything. It still needs an operator at some level, but it is mostly automated. As it turned out, that was a really, really good thing, because what that automated software allowed us to do was be pretty resistant to the COVID pandemic affecting operations. And I'll come back to that in a minute. But the mission has largely been unaffected by the COVID pandemic, thankfully. Okay, enough about what Cheops is trying to do. Let's have a look at what it is doing. This is the image that was on my title slide, and this is an artist's impression of Cheops in orbit. But let's have a look at it in reality. This is a real image of Cheops in orbit, taken from Geneva last January with a 70-centimeter telescope. And if I zoom in, you can see the satellite trail of Cheops transiting the bright star Eta Aurigae. So this is quite cool. We can see our satellite from the ground. We can check that it's there. We know it made it into orbit, thankfully. and everything seems to be good. Speaking about making it into orbit, Cheops was launched in December 2019 from French Guiana. It was a pretty challenging launch. It was a busy launch. This is Cheops being fitted into the launch vehicle. It wasn't the only satellite in that vehicle, in that rocket. There were 5 satellites, 5 passengers on this rocket. And as you can tell from the respective size of these stickers, Cheops wasn't the main one. Cheops was in fact the second passenger. The main passenger was an Italian defense satellite. And then there were these 3 other smaller scale things as well. And they all sort of squeezed into the fairing of this rocket, this Soyuz, like so. The launch was actually delayed by 1 day. In reality, there were some slight technical issues with the rocket on the day that Cheops was supposed to launch, but a day later, the launch went ahead successfully. A few hours after launch, Cheops was injected into low Earth orbit. It's about 700 kilometers altitude, and it more or less orbits along the terminator. So it's not a geosynchronous orbit, it's more of a sun synchronous low Earth orbit. Most ESA missions are controlled from Darmstadt in Germany, but the Science Operations Center for Cheops is actually at the Observatory of the University of Geneva. This antenna on the roof is a decoy, as I've pointed out here. The actual communication goes via an antenna in Madrid, but the operations themselves are performed and organized by a small but dedicated team of 4 people at Geneva. So here they are, working away, making sure that everything is going to plan. So December 19, 2019, Cheops launched. Everything went according to plan there. It was inserted into orbit. But what's been happening since? Well, I'm going to talk through some of the key milestones to show you what's happened. So it was launched just before Christmas, and it was sort of left to rest over Christmas and acclimatize to space. The instrument was switched on early in January last year in order to take some dark fields with the lens cap on. They looked fantastic, looked perfect, exactly what we were expecting, so that was good. And so at the end of January, we opened the lens cover because it's not much use just taking darks all the time. So we took the cover off and did some measurements of the point spread function. Now this is a slightly unusual looking PSF. It's not circular. There is a reason for that. It's expected that it looks like this. So the mirror on Cheops is fixed at 3 points around its circumference. The reason it's fixed in that way was to limit the strain and try and prevent the mirror deforming during launch, because at the time the satellite was designed, we didn't know what the launch vehicle was going to be. So it has this quite strong fixing, which gives this slightly odd shape. The point spread function is also defocused as well to distribute the light from the target star over more pixels. The reason for doing that is that it helps the precision of our photometry. By spreading the light over more pixels, we make it less sensitive to the small differences between individual pixels on our camera and to the variation in the pointing of the spacecraft, because it doesn't point perfectly. It does, in fact, point slightly slightly vary its pointing. So you want to limit the effect of that if possible. Now, although this PSF looks slightly odd, it did in fact match really nicely the theoretical prediction on the right here of what that PSF should have looked like. In fact, it turns out to be slightly better than the theoretical prediction, so that's fantastic. So everything, again, seems to be going well, but as with all space missions, it's not enough for us to just look at our PSF and take an image and say, okay, great, let's get on with it. You have to commission the whole satellite. So there was a very thorough commissioning process, checking all the systems, checking that everything is working successfully, because we can't go and fix this satellite. It's not like a ground-based observatory, obviously. Once it's up, and it's very difficult to do anything about it. But I'm happy to say that at the end of March last year, 25th of March, the commissioning was declared successful. Now, that date, of course, is about the same kind of time that the COVID-19 pandemic was really starting to shut everything down. As I said, thankfully, we weren't too badly affected by that, although it did put a slight strain on some operations. Before Cheops launched, there'd been several studies of what the performance should be. So they were all published early 2020. Once we had launched, and as part of this commissioning process, we had to check that the performance matched what we expected. So this is a 47-hour sequence of images of a magnitude, visual magnitude 9 star, created or obtained by the Cheops instrument scientist, Andrea Fortier. I could sit here and watch this for a while. It's quite mesmerizing. From that sequence of images, we can extract the photometry, and we get a nice light curve like this. So it's pretty stable. There's a bit of variation up and down long term. You can sort of see maybe some variation going on here, intrinsic to the star, and you can see the individual variation between measurements that's expected, the noise in our measurements. But this is pretty good. We can extract the photometry from the PSF, and we can then sort of look at the average noise in this light curve. So if we look over a 6-hour period and do a running average, then we get a mean sort of noise value of about 11 parts per million. Now, Cheops was required to achieve 20 parts per million. So the actual performance on a magnitude 9 star is about twice as good as it needed to be, which is great. The reason that's particularly exciting for bright stars is that that mean noise is a rough estimate of how shallow a transit can be detected. Anything that's more shallow than that starts to disappear into the noise. So at 11 parts per million, we're starting to get into pretty shallow transits, which means big radius ratios between the planet and the star, which means on a sun-like star, a smaller planet. So we're starting to get into smaller planet territory here, which is great. Unfortunately, not every star is magnitude 9. So here's an equivalent light curve for a magnitude 12 star with the images on the right there. This gives us 75 parts per million. So as expected, it's not as performing as well, but it is still better than the noise requirement that we had, which was 85. So by all measurements, Cheops is performing better than it needed to and than it was expected to. So I think we'll call that a success as far as we're concerned. So those are some flat light curves the real test, the real exciting test was to observe a known planet and see what kind of results we could get. So we tried Cheops out on the transiting planet Kelt 11b. So this is a gas giant planet, a hot gas giant planet close in, transiting a subgiant star. One of the reasons this was picked as our first target is that the transit of Kelt 11b is quite long. It's about 7 or 8 hours, which makes it quite tricky to observe from the ground. And you often have to stitch 2 half transits together, or just observe half by itself. But with Cheops, we could observe the full transit and get a light curve that looks like this. So the light blue points here are the actual measurements from Cheops. The larger, darker points are those measurements averaged into bins of time, just to reduce the scatter. You can just about see in green in the background here, the model fits to that data. And then at the bottom here, we've got the residuals from the measurements. So how an indication of how well the model is fitting to the data. And you can see that these residuals, they do wobble up and down a little bit, which in some cases might indicate that your data is not very good. But in this particular case, these are actually pulsations from the host star, from that subgiant. It's pulsating in brightness, so we're seeing these pulsations in the Cheops data, which is quite exciting. Given that the key point about Cheops is to measure planet radius really precisely, we want to know how well we did. So if we look at Kelt 11 from this data, on the inset in the bottom right there's a visual indicator of how precisely the radius of this planet was measured. So we measured it to 90,500 kilometers, plus or minus about 1,700. That's just under 2% precision, which, given that the radius precision from ground-based surveys is of order 5% around really bright stars, 10% even higher than that, 2% precision is fantastic on a radius. And it indicates that Cheops can really do what it's supposed to, and really dig down into these radii in order to help us get the bulk density. So that was quite cool. It was a known transiting system. It was an improvement of radius precision. It's exactly what Cheops was designed to do. But Cheops had these other goals as well. These other things that would be new discoveries relating to known systems. So I want to talk about 3 Cheops discoveries so far in particular. The first one was something that was part of the early program for Cheops observation. So something that was identified pretty early on as a target we wanted to focus on. And that's WASP 189b here. So this is another close-in giant planet. It's about 7 million kilometers away from its host. And what we saw with Cheops here was not only the transit of the planet in front of its star, but also the passage of the planet behind its host star. So when the planet goes behind the star, you also lose a small amount of light from the system. When you're seeing both objects together, you're not only seeing the intrinsic light from the star, but you're seeing reflected light from the planet. And of course, when the planet disappears behind the star, you lose that reflected light. These close-in giant planets are generally thought to be tidally locked. So the same face of the planet is always facing the star. We refer to that as the day side, as opposed to the night side, which faces away. And the depth of this occultation, this passage of the planet behind the star, gives us an indication of the temperature of that day side, of the reflecting side of the planet. And in the case of WASP 189, this is indicative of a temperature of just over 3,400 Kelvin. That's incredibly hot. It will vaporize any cloud on the planet, including metallic clouds. So metallic species in gaseous form will be completely vaporized. So this is a pretty hot, extreme environment, is what I was looking for. We of course observed the main transit, or the primary transit of the planet. And here as well, we saw something quite interesting. I mentioned that one of the goals of CHAOPS was to observe subtle variation in transit light curves for things like moons and rings. With this planet, we saw a subtle variation in the transit. Over here on, you can see two fits to the data. You've got the green line, which you can just about see here, which is a fit assuming the star is spherical. But the actual best fit to this data is the red line. So this is an asymmetric transit, which indicates that the star is non-spherical. So this star is rotating fast enough that it is no longer spherical, and visibly no longer spherical in our data. These kind of tiny effects weren't very often seen before CHAOPS. So this is another really interesting result, and really shows the power of the CHAOPS instrument and its capability. It was also quite well received. It was publicly announced last September through a Swiss press release and a news article. Did quite well in Switzerland and sort of made the news rounds in several other countries as well. And that's just a selection of headlines and articles relating to this planet. The second result I want to focus on really highlights one of those other science goals of CHAOPS. So here we're observing, test object of interest number 1233, otherwise known as HD 108236. On exoplanet names, wonderful. Here, this was a system with 4 super-Earth planets, so terrestrial planets bigger than the Earth, and it was detected by TESS. And what CHAOPS did was observe these transits of these known planets, and improve the radius precision and improve our knowledge of the orbits, of the periods, of the times of transits, and of the other orbital parameters. On this plot, or this light curve on the right here, you'll also see this transit here, which at first glance might look like another transit of planet E, similar to this one, but it wasn't. It didn't match up with the orbit of planet E. And what it turned out to be was a previously undetected planet, planet F, in this system. This planet hadn't been detected by TESS, but by combining the TESS data with the CHAOPS observations, we were able to validate that planet and confirm that it did exist. And so CHAOPS has added a 5th planet to this system, which was, as I said, one of the goals of the mission. The third result that I want to show you today is this very special system, TOI 178, so TESS Object of Interest 178. This was known to host 2 planets from TESS observations. And again, CHAOPS found more planets. It actually found 4 more planets. There are at least 6 in this system. And the 5 outer planets are in resonance, similar to what we see with Io, Europa, and Ganymede. The 5th planet out, the one that's shown here in grey, was not initially detected by CHAOPS. It was found by using the resonance chain of the other planets and then predicting when it should transit. And then when Cheops observed at that predicted time, sure enough, there it was. So this is quite a cool system, 6 planets, 5 of which are in resonance. The pattern is 18 orbits of the second planet to 9 of the third, 6 of the fourth, 4 of the fifth, and 3 of the sixth planet. So you can see here they orbit in resonance. And so every few times one of the planets goes round, one of the outer planets is orbiting and lining up with it. So this is quite an interesting system. There are not many resonant systems known, and this one is unusual in that the densities of those planets don't actually follow any kind of pattern as far as we can tell. In most resonant systems, there is some kind of pattern to the densities, not so in this case. So those are 3 of the key Cheops results so far, which, considering the mission has been fully operational for just over 1 year now, is pretty good going. There's some exciting science there, and there's lots more to come. I wanted to finish off my talk today, having discussed Cheops in one of our current missions, to look ahead to the future a little bit and sort of riff off what Roger discussed in terms of habitability and biosignatures. So he briefly describes several of the various space missions we have, looking to probe the makeup of exoplanets and their atmospheres. We have James Webb, which will hopefully launch this year, finally, Plato in 2026, Ariel in 2029. Now, one of the key drivers for several of these, or for all of these, in fact, all 3 of these, is habitability, which of course is a topic that fascinates a lot of people. It's been the subject of philosophical and scientific debate and discussion for millennia. It's a popular trope of science fiction. A lot of astronomers or professional astronomers are inspired by science fiction. A lot of amateur astronomers are inspired by science fiction. Interestingly, a lot of my colleagues at Warwick say that their interest goes the other way. They were interested in astronomy first and then became interested in science fiction afterwards. So it does work both ways. But this concept of habitability in other worlds that are habitable and potentially could support life really sort of gets people thinking. Unfortunately, we don't really have a good estimate for how many habitable planets actually exist. This is 12 estimates for the Eta Earth statistic, which is an estimate of the number of habitable planets per star. All 12 of these were calculated from the same data set, all from Kepler data, and they all considered the same types of star, so F, G, and K dwarfs. And yet the estimates here vary by a factor of 100. So what's going on here? Well, there are 2 problems. The first is your definition of habitable planet. Between them, these 12 studies used 8 different definitions of habitable planet, all of them based on the radius of the planet. So that's one disagreement among researchers. The second reason for this large range is the definition of the habitable zone. So the concept is relatively familiar. It's the orbital distances at which surface liquid water could exist on a planet. And there were 10 different definitions of this habitable zone used between those 12 studies. So we can't agree on what a habitable planet is, and we can't agree on what the habitable zone is. So how can we agree on how many habitable planets there are? Well, that's a tricky discussion to have. We have found lots of planets that are potentially habitable. This graph or this graphic shows those that are terrestrial and in the habitable zone. But all of these are around cooler, smaller stars than the sun. Through all of the systems found so far, we have not yet found a precisely characterized Earth analog, by which I mean a one Earth mass star, or one Earth mass planet orbiting around a sun-like star with a period of about a year. We haven't found that yet. This is difficult. This is really difficult. And this is one of the reasons why Eta Earth is so uncertain. TESS will struggle to do it. Cheops might do it. Cheops has the precision to be able to get the radius of one of these planets, but it does need to know when and where to look. Because it is a follow-up mission, Cheops needs to know what it's looking at in order to get that radius precision, which means it needs radial velocity measurements to get the mass and to tell it what the orbit is, or a survey to find it first. That's sort of where the Plato mission comes in, that Roger mentioned. So one of its main objectives is to discover and characterize terrestrial planets in the habitable zone of sun-like stars. Like Cheops, it's a photometric transit mission. Unlike Cheops, it is more in the mold of TESS. So it is a survey mission looking for new detections, new planets. In some ways, Plato is sort of a Cheops inversion. So Cheops is a follow-up mission to look at radial velocity systems and find transits. Plato is a transit detection mission which will have a dedicated team to perform radial velocity follow-up to get masses. So in that way, Plato also gets us to bulk densities with good masses and radii. Discovering Earth-Sun analogs is not going to be quick. It's not going to be easy. We're pretty confident that those systems exist statistically, but finding them will take time. You need time to build up the radial velocity observations to generate the mass and be sure the planet is there. And when your planet only transits once every year, if by some misfortune you miss one transit, you're stuck waiting for the next one. And that's a real potential problem. But let's assume we find them. As Roger talked about, we want to then find out, are they habitable? Could they support life? And there are two missions currently being studied by NASA that could really advance our understanding in that area. Selection of one of these, if it happens, would take place later this year. They are competing against two other concepts which have no exoplanet science in their program, but there are these two concepts being discussed. The first is LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, so another wonderful astronomy acronym. There are actually two concepts being discussed for this mission. One has a 15-meter mirror, and the second one has an 8-meter mirror, depending on how much money is available and how complicated the mission wants to get. Proposed launch date for this is 2039, so 10 years after Ariel, and it's a similar concept to James Webb, but scaled up and with correspondingly greater capability. And as a big part of its science program is examining the habitability of exoplanets and looking for biomarkers. It has a coronagraph to block out starlight so that it can image faint, potentially Earth-like exoplanets. Those images would be a few pixels only of those planets, but from that, the idea of LUVOIR is to be able to learn about the planet's color, its atmospheric composition, and potentially even map the surface of the planet as it rotates. As I said, habitability is a key part of the science program proposed for LUVOIR, and they have this 10-step plan for trying to detect biosignatures and biomarkers, things like water, ozone, carbon dioxide, oxygen, or methane in the atmospheres of planets. So they've really thought about it in great detail, and they really want to push ahead with it if the mission is picked. The second concept that NASA are considering is HabEx, which, as the name suggests, Habitable Exoplanet Observatory, is very much exoplanet focused. It's a similar kind of idea, but a smaller mirror. It's a 4-meter mirror, optical and infrared, and it's again got a coronagraph, a star shade, so that it can directly image exoplanets and look at their atmospheres to look for those biomarkers. It would launch slightly earlier, maybe 2035, but as James Webb shows, launch dates are fickle things and prone to delay in significant ways, particularly with these big missions. So that's sort of where we are. It's an exciting time to be researching and studying exoplanets. CHAOPS is just one of several recent advances that have opened up the field, new areas of the field to explore. CHAOPS is a fantastic mission that, as I showed, is giving us some real new insights and showing us things that we hadn't been able to detect before. And I think the future is bright for exoplanet research. I think the potential for detecting biomarkers is good. People are actively thinking about how to do it. CHAOPS might not get there, but we will eventually. And as we think about that, ultimately, what do we want to learn? We want to learn about ourselves and Earth and how we are affected. So thank you very much.
Thank you, David, for a fascinating talk. It's really amazing to see what CHAOPS is achieving in the increase in precision and sort of tying down those radii of the planets. Just to re-emphasize, you can ask questions in the Q&A on Zoom, or if you write a comment on YouTube, and we will be reading out the questions and doing the answers, so that hopefully you shouldn't miss anything if you're listening on YouTube. So the first question we've got is from Adrian Jones, and he's asking, given the detection bias in favor of relatively planets with short orbital periods, what can we say about systems that are more like our solar system? With a follow-up of what he said is, I mean, what can we say about how frequently they occur?
Yeah, that's a really good point. There is this strong detection bias. Let me stop sharing my screen actually, so you can see me. There is this strong detection bias. You're absolutely right. The closer a planet is to its host, the more regularly it transits, so the more opportunities you have to find it. A lot of the studies looking at E to Earth sort of make certain statistical extrapolations from what Kepler has been able to see and what TESS will be able to see to try and extrapolate to systems more like the solar system. Kepler helped us in this sort of area because of its 4-year stare at the same patch of sky. So that allowed detection of longer period systems. So we were getting closer to Mars-like orbits, for example. Not quite to Earth-like for a few reasons, but we're getting closer to that. There are definitely biases in those estimates. That's another reason why I think a lot of them are quite varied. have to admit, I haven't dug too deeply into the statistical biases myself for these studies of Eta Earth. I think guessing or working out how many potential solar systems are out there is a bit of a guess still. It's very much an extrapolation from incomplete data. So we're confident that there are some, but the exact number is up in the air.
Thanks, David. The next question comes from Mill Dave. He says, will the Cheops mission be making use of the maturing Ariel database that's contributed to by amateurs and professionals?
I don't know the answer to that one, I'm afraid. Yeah, I don't know. Sorry.
Fair enough, honest answer. I'll switch over to a question from YouTube now, which is from Owen Gwynn. He says, I think Kelt is my favourite telescope name, but I'm not sure why it is called kilodegree telescope, as the field of view is 26 square degrees, which is only 676 degrees.
Yes, I remember asking the lead of Kelt why it was called the kilodegree, and I cannot remember what they said, unfortunately.
It isn't the usual rounding you get in astronomy to the nearest significant figure.
I mean, that seems quite plausible. We do like to round quite a lot, don't we? Yeah, no, astronomy acronyms are great things. They really are.
Yes, I think there's a kind of a whole sort of art form to naming telescopes these days.
Mm-hmm. Yep.
So then, final question at the moment is from Dal Dobbs, and he's asking, how often is the observing schedule updated for targets of opportunity or new discoveries?
How often do we... Just looking double checking something here.
To get an actual live answer as it is now.
Exactly. So for like most ground-based observatories, Cheops, because it's this kind of follow-up model, it takes observing proposals from potential users. So people put forward science cases to request time on Cheops. So in that respect, the observing list or the target list is updated based on what people have asked to look at, and based on which programs the science committee, the time allocation committee, think would make the best use of Cheops. Those proposals primarily can't be submitted whenever you like. There are specific calls for Cheops proposals, and I was just trying to double check the frequency of those. Usually it's around every 6 months or it's every year. Annual, there we go, I found it. Just double check, yeah. So it is annual calls for guest targets. There is a certain amount of time that is set aside specifically for the consortium to use, and they have their own target list. That target list is updated fairly regularly based on new discoveries that look interesting and that fit into Cheops's capabilities. So that one is more sort of a living target list as opposed to the annual update from guest programs. There is, for many telescopes, something called discretionary time, where if you have a particularly exciting result that has to be observed now and it can't possibly wait, a supernova, for example, goes off and you want to look at it, you can put in a proposal to observe it then and there. Cheops, as far as I'm aware, doesn't have discretionary time allocated to it. I'm not completely 100% sure that that's the case, but I'm reasonably sure it doesn't have discretionary time. But so the target list sort of updates fairly regularly and is based on what people want to do with it.
We've had a couple more questions come in.
Sure.
One is from Viktor Popov, and he's asking, is there any planet size in terms of mass radius that would be considered suitable for harboring life? Should emergence of life be able to circumvent the size of the planet?
That's a really interesting question. And it's sort of, So there is a limit. There is an inherent limit on the size that a planet can be and remain terrestrial, at least as far as we know based on the data we have now. So once a planet gets beyond a certain size during formation, it tends to start to dominate the disk and start to accumulate gas and slowly sort of turn into a gas giant instead of remaining a terrestrial planet. So there is that inherent size, sort of size constraint. But that answer sort of fundamentally assumes that life can only exist on a terrestrial planet, which, based on what we know, is the case. But then you can sort of start to get into interesting science fiction considerations of what kind of life might exist in the atmosphere of a gas giant, for example. And you also start to get into things like the moons of Jupiter or the moons of Saturn and what might be living under the surface in the oceans of some of the icy moons. So I think if you stick to terrestrial objects, there is a radius and mass restriction there. But I think the stronger limit it would be what the surface conditions are like rather than the size of and mass of the planet itself.
Good answer. Then final one at the moment is from John Morrow, and he says ESO were attempting to detect planets in the solar system using the radial velocity method using their HARP spectrograph. Last time I saw any results, they had failed to detect any solar system planets. Have they now found any?
Solar system planets.
Yeah, I wasn't quite sure. John, do you mean perhaps a solar system similar or a planetary system similar to the solar system using the HARP spectrograph rather than planets in our solar system? Or I'm trying to think. I think I may have recalled that there's a clone of the HARP spectrograph being built to detect Earth-like planets. But
yes,
that I don't think has gone live yet, or is about sort of going live at the moment.
Yeah, so okay, so you've got the original HARP spectrograph in Chile on the ESO. Okay, thank you, John. Yes, I know what you're talking about. To finish that point though, there is a clone of HARPs already on La Palma in the Canaries on the Gran Canarias telescope. But there is a third clone which is also being put on La Palma, which would be dedicated to finding terrestrial Earth-like planets. Yes, that is you're right, Andrew, that's not yet operational. The last I heard from that project was a couple of years ago now, and they were trying to sort out the funding for the situation for that. The fact that I've not heard anything for 2 years is more a fault on my end and not keeping up with the project rather than any indication that it's in trouble, I should stress. John is talking about the solar.
Yeah, I think he's added a follow-up which has said that it's to do with the Helios Telescope to look for planets in our solar system.
Yes, so this is quite fun. So HARPS is attached to the 3.6 meter telescope at La Silla Observatory, but right next to it, or on one of the platforms, they've got a small solar telescope, the Helios, and they fed a fiber from that solar telescope into HARPS to collect data, on the sun. And John's absolutely right. The idea is to observe the sun as if it was an exoplanet host star, in order to learn about stellar activity, star spots, plages, flares, and how that affects radial velocity observations and measurements. Trying to remember exactly what they found with this. So that I know they collected an awful lot of data with this experiment, and they did indeed detect Jupiter for a start. They had quite a lot of fun trying to pull the solar signals out of that data, actually, because they had to deal with effects from the Earth's orbit. They found a really strong signal that turned out to be Jupiter, if I remember correctly. And they started then sort of digging around in various other small scale effects. I don't think they detected any of the solar system planets other than Jupiter, but I'm not sure if they have or not. I mean, it's a small telescope, but the data is really quite good. So,
and is the main goal of this to kind of simulate what we're seeing when we observe exoplanets with the radial velocity methods, where you've got a star right up close, so you can see what the star is actually doing.
Exactly. Because as we get into instruments like Espresso, or we start to need to look at signals that are sort of centimeter per second level, which is what you need when you're trying to find an Earth around the sun, then the effects of activity of your stellar variability, inherent variability, start to become quite important. And so, yes, that's the idea, is to try and study a star up close, so you can see how those affect it. Yeah, Andrew, exactly. Published paper. John's asked if there are any published papers from the project. I have seen data from that project, and I've discussed data from that project. I'm sure there was a paper published on it, but I would need to try and find it. I don't remember off the top of my head who it was by. I have a strong suspicion I know who it was by, but I would need to check. But I know the data exists, and I know they were studying it quite closely and trying to find those signals.
Great, thank you, David, and thanks again for a very informative talk on Cheops and all the exciting things going on in exoplanets.
Thank you.
So what we'll be doing is we'll now be closing up for this session, and then restarting at 7:30 when we have Dr. Jesse Christiansen giving the lecture on an exoplanet far, far away, which is the Alfred Curtis Memorial Lecture. And I see Alan's rejoined.
Yeah, thank you very much, David, and thank you very much, Roger, for his presentation as well. And as Andy said, we're all going to come back here at 7:30 to see more presentations. And that's going to be the Alfred Curtis Memorial Lectures, which has been traditionally done. And she's going to be Zooming from America live. And I think the last time we've actually at Winchester weekend, we actually had an international connection, is when we actually used the Helios Telescope live in the lecture theatre, which was quite exciting. So anyway, let's see you all back here at 7:30.
Thanks all.
Okay.